Okay, so um, right, we are continuing our session on theory of databases, namely relational algebra, which is a way to take relations, which are kind of like tables, but with some extra stuff, and how to manipulate them. So, how to take two or more relations and add them, subtract them, multiply them, um, these kinds of things. The point of this is to be able to write queries, to be able to take lots of um, different parts of data and combine them together in order to uh, narrow down data to match certain requirements that we have. Let me go back here. The last class, I talked about viewing relations as tables and also about viewing them as sets. Both are valid. Sometimes one view is more useful than another. So, as far as viewing these things as sets, last class I started to talk about some basic set theory. This included some notation as far as how we write sets, namely in between these sort of squirrely brackets, that indicates that we're talking about a set, and elements. A set is made up of or a set is a collection of things. This collection is separated by commas. And fine. Sets have a certain size. That's the number of unique elements in them. Here we're talking about set size. And I believe we ended talking about these things. Yeah, sets are a collection of unique things, basically. Okay. Now, okay. So now I'm going to be going over operations that you can do with relations. So like regular algebra, there's addition and subtraction and multiplication and division and other stuff that with numbers, if you were taking an algebra class, you would learn what does it mean to add, what does it mean to multiply, to divide, and blah, blah, these numbers. Here we're going to be learning about different symbols and what they mean with respect to relations. Some of these symbols will be the same as you've seen in algebra, and the operations are a little different. Other symbols might be new, but there's not so many of them. In fact, I think it's 7 altogether. Okay, technically 8. But let's start going through them. So the first operation is a union. Stop my video. Okay, great. The first operation we have is a union. That's written this way. Where this symbol means union. This is something akin to addition, and I'm going to teach some more notation. This is a set, so curly brace. Let's see here. So this is the set of all x. This vertical line means such that x is in A, or x is in B. Just a minute. Great. So this is a union. This is a sort of, this is a mathematical shorthand for defining a set. Again, these curly brackets indicate that we are talking about a set, a collection of things. And this is a set where every element of the set is either a member of A or it's a member of B. And this little sort of E looking thing means that is a member of, I guess. There's a more pictorial way of viewing this, which is if we have some set A and we have some set B, A union B is like this. So, so long the member X, it can be an A, it could be a B, or it could be in both of them. Doesn't matter in any case. We're taking these two sets, A and B, and kind of combining them together. Okay, so that is a union. And this is something that exists with relations and with sets, this symbol. But this is not a symbol that exists with just numbers, right? 4 union 5 doesn't really mean anything. So this is an example of a symbol. It's one of the basic operations that you can do with sets. And fine. The next we have an intersection, which is written this way, with a cap, I guess. And this is also a set of all x such that x is in A and x is in B. That is like this. Those elements that are both members of A and members of B. Okay, we have the set difference. Okay, now here for the first time we're using a symbol that you've seen in algebra before, the minus symbol. Here, it's not subtracting one number from another, it's subtracting one set from another set. And what this is it's a set of all x such that x is in A and x is not in B. So this symbol here means it is not an element of. So you write this sort of membership thing, and then if you put a cross through it, that negates it. So this means things that are in A but not in B. So in particular, that's these sorts of things. Again, I'm writing these images to the right. That is one way of viewing sets as sort of a collection of things. So here A is, I'm writing a circle to represent that it's a collection of things, and there would be many different members all inside of A that would comprise it. It's just a particular visual way of representing sets. I will go back and forth between these. So for union, X is in set A or B or both. Correct. If X is in A, or X is in B, or X is in both of them, then X is included in the set. That's the union. Okay. Now, let me turn on my camera here. Okay. So, these are the more basic operations. And let's see. These three operations, these work on the same kind of relation or tuple. Okay, so here's this word tuple, which is a new word. If we take the table view of relations, then maybe we have an SID and a name and an age, something like that. Okay, and this is, I don't know, a relation we'll call students. A tuple here is actually not the name. It's a tuple is this part. So here, this tuple for this table is the triplet SID, name, and age. So these three operations work when the relations are of the same kind. So that is to say that here, if I have another relation, SID, name, age. Okay, so now I have two different relations. They have different information, potentially. Like here's John, or I don't know, here's SID 1111, 2222, and now here's a different SID. Blah, 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 blah. Okay, these are of the same kind, meaning that they have the same number of columns and basically the same columns. Now for these, we can union them together. Okay, that is sort of, that would be taking these entries and kind of appending them to the bottom. Okay, so you're lengthening the table. That's the effect of a union. You can intersect them. Okay, so here is an entry with 222. There's also an entry with 222, and so we would get out something with also the entry 222 for SID, right? So we can intersect them, union them. We could take the set difference between them. So if we write a minus between these things, well, here again is the same type of entry, and so that would maybe go away, and we'd be left with 1111 and blah, and 3333 and blah. And that's what I mean, that they work on the same type of relation or the same kind of tuple. Again, the tuple here is the generic triplet, that it's an SID, then a name, then an age. It's the name and type of the columns. Okay? So all three of these, they work only when the two relations are of the same type. Now, so for example, for subtraction, here, this works. I can subtract this relation from this relation. I can subtract the one on the right from the one on the left. But if I had, I don't know, favorite movie here, like this, this does not work. Now I cannot. This does not work. Why? Because one of the relations has another column, favorite movie, where the other one doesn't. And so now you cannot subtract them anymore. You cannot union them. You cannot do a set intersection because the types don't match. Is a tuple a list? No, a tuple is written like this. I don't know, alpha, beta, gamma. So this is a tuple. A tuple is it's like a set, except order matters. So where things come it's a set, but where order matters. That's a tuple. It's kind of like a list. Yeah, it's kind of like a list. But But here, I mean, so this tuple would be SID, name, age. Okay, this is a tuple that describes this, where this would be, you know, an integer, I guess. A name would be a string, and an age would be, I don't know, also an integer. So this is a tuple. It includes name and type. I'm not on purpose introducing new vocabulary for things. It's not a complicated idea. Here, a tuple is just if you take the names and types of the columns. There happens to be a word for that, and it's called a tuple. Okay. All right. So these first three operations, that's the union, the intersection, and the set difference, the objects that you're applying this to, if it's A union B, well then A and B have to be of the same type. And of the same type, what I mean is that the columns have to be of the same types. So here we have an SID that's an integer, a name that's a string, and an age that's an integer. And so that works, so long as both of these relations have all of the same, have the same number of columns, and the types of the columns are the same. Again, here is an example where this would not work because this relation on the right has an extra column, favorite movie. And because now the number of columns are different, you can no longer subtract. There is no set difference that you can do here. It's sort of a nonsensical attempt to use this operation. It doesn't mean anything. If the left table had the extra column, then yes, it would work. If this also had a column favorite movie, now everything is okay. Because now the types here, they all have 4 columns, they're all the same type, and so yes, now this is okay. Okay. So those are the first 3 operations. Right? I mean, if the left table had a column, but the right one didn't, as in, does order matter for subtracting? Okay. So if we had this, would this work? And no, this would not work. This would also break things, because now here there's an extra column that this table does not have. And therefore trying to union them together, trying to come up with their intersection or their set difference, you can't do. Because the types of the 2 relations are different. Order, does order matter for a subtraction? Yes, you will come up with 2 different results if you subtract. I mean, A minus B is not the same as B minus A. Those could lead to 2 different answers. In addition to that, it holds the same that for A or B, they have to have the same number of columns and the same types of columns. So here, this will not work because here there's an extra column that this one doesn't have. No fave movie column. So this will no longer work because the relation on the left has 4 columns, the relation on the right has 3 columns. It doesn't even matter what the columns are at this point because the number of columns is different. Already it's not going to work. Okay. Any more questions about the union intersection set difference before I talk about the other operations? Okay. Okay. So the fourth operation that we have is the cross product. Okay, this is when you multiply 2 sets together. A cross B. Okay, when you multiply 2 sets together. Now, this is different than multiplication with numbers. And here, these are all possible pairings between A and B. So let me give a quick example of this. And now here, also, the 2 sets don't even have to have the same type. They can be completely different kinds of sets. So just to emphasize that, let me make a smiley face and a frowny face. Okay, so A and B, they have different sizes. The size of A is 3. The size of B is 2. Also, their types are very different. A is a collection of names. B is a collection of, I don't know, emojis. So, here, let me write this a little different. John, Peter, Paul, smiley face, frowny face. Okay. So A cross B are all possible pairings. And here it doesn't really matter if A comes first or B comes first. Let me start to write this out anyway. So okay, John, who's in A. We're going to pair John with every element of B. So John is going to get paired with the smiley face and with the frowny face. So there's the first element of John. I'm sorry, the first element of A cross B and the second element of A cross B. Okay. Now I'm not finished. I've still got some things to write, but there's a couple things to notice. First of all, these are 2 elements in the set. Okay? So the set, I'm using this curly bracket to indicate that it's a set. Recall that elements of a set are separated with a comma. So here, so far, I've written down 2 elements of the set. This is one element. Now this one element, again, we know it's one element because it comes before a comma. All of the elements of a set are separated with commas. Now, this is, I'll say it's a vector of 2 dimensions. It's a T, right? Dimension? Dimension, yeah. I think it's a T. Okay. So now I'm using another word, vector. You might have learned, or you might have heard of the word of vector in a linear algebra course, maybe a physics course, things like this. All that a vector means is, I don't want to make things more complicated than they have to be. It's a very simple idea. Here, one element has 2 parts to it. It's like saying a point in a grid that has an x and a y coordinate. And so if you're talking about a point in a 2D plane, then you need to know both its x coordinate and its y coordinate. Here, this would be a name coordinate and an emoji coordinate. Okay, so this is something like a point in 2 dimensions, where one dimension is a name dimension, and then the other dimension is an emoji dimension. So these 2 elements, while they share the same name in the name dimension, in the emoji dimension, one has a smiley face, the other has a frowny face. So they're 2 distinct points. And these points are made up of more than one thing, which is why it's called a vector. A vector it's still a single point or a single element. If I were to draw this as a set, A cross B, then here I could have a single point, but this point is 2-dimensional. This point might be, John Smiley Face. And now here's a different point, which is John Frowny Face. Okay, so within the set, it's a collection of elements. Here, each element has 2 parts to it. It's a 2-dimensional thing. So you can talk about higher level dimensions, and it should not be scary, I guess, or confusing to talk about this. All that this means is the number of items that comprise a unique element of the set. Okay, that's enough about that. Let me go ahead and finish up what this looks like. So A cross B. Again, here we have A, that's John, Peter, Paul, and we have B, which is a smiley face, frowny face. The cross product are all possible pairings. So far, we've paired John So these are all of the ways that you can pair element John with elements in B. If we continue, there's also Peter that can be matched up with these. So we'll have Peter smiley face, Peter frowny face. Okay? And now we've matched up, we've done all pairings with John that we can do, and we've done all pairings with Peter, and now we do all pairings with Paul. So we'd have Paul happy face and Paul frowny face. And that finishes the set. Okay? So we have 6 elements all together, because the 3 elements of A each get paired with the 2 elements of B. So that's 6 all together. I will also say that these 2 are considered the same. So that is to say here, John smiley face is the same as smiley face John. Okay? It doesn't, the order of these things don't matter. And whether you pair every element of A with B, or you pair every element of B with A, same thing. You'll in each of these you'll get back, in this example, 6 different elements. So this is one of the more complicated operations. It's not really too complicated, but it's more complicated than a union intersection set difference. So let me pause and see if there's any questions about this, about how a cross product works. None. Okay. Then I will pick out on a student to help me work through one of these. Okay, how about AJ? Got a mic?
Hello?
Okay, hey. So I'm going to give 2 relations. One called boys, one called girls. And here they'll both have name and age. Okay, so for the boys we have John, who's 18, and Paul, who's 20. And for the girls, we have Susan, who's 19, and Anne, who's 21. Okay, so these are 2 relations, and now I want to cross-multiply them together. So this is going to be the relation boys times girls. And yeah. So first of all, what are the columns for this relation?
So would it just be like name versus age for both?
for both.
Like earlier, we had name and emoji, and that's like what we crossed. But here
Oh,
for boys and girls, there's name and age.
right. So you said a name and an age for both. You mean like this?
Mm, not exactly sure. I guess like what's different for me from the last example is like in this case, boys and girls have like two attributes to them,
Yep.
whereas like earlier in A and B, like it was just name and emoji. So I'm not sure like how they'd be like categorized here.
Okay. Well, I'll give you a hint. It does go like this. Although they both have a name and an age column, um, one is, this name, for example, are boys' names. This name are girls' names. So implicitly, they're a little different. Implicitly, not explicitly. So this is the way that the table will look. Let's see if we can get the first entry. So again, this is all possible pairings.
Okay,
So yeah. Mhm.
so would the name and age like entity for like say like John, so like
Yep,
John 18, that would be like one of the things that I would group. So a possible pairing would be like John 18, Susan 19.
that works.
Okay.
So what that would look like is John 18, Susan 19. Okay.
Um, so then you could also do like John 18 and 21.
Okay.
Um, and then I guess the same with Paul. So Paul 20, Susan 19, and Paul 20 and 21.
Great. Paul 20, Susan 19, and oof, Paul 20 and 21. Very good. Yeah, that's it. Very good. That's the way it works, just like this. So, okay. Let me ask. How about Indira? Indira?
Hi, Professor.
Hey, how are you?
Good, how are you?
Okay. Um, let's say if I had a table A where the size of A is 10, and then I have a table B where the size of B is, I don't know, 5. Then what would the size of A cross B be? So A is a table with 10 rows. B is a table with 5 rows. How many rows
hmm
does the table A cross B have?
Um, would it be 50?
50. Yep, perfect. Excellent. Wonderful. Okay, just a sanity check kind of question. Beautiful. Thank you very much.
Of
So,
course.
uh, cross products can be kind of expensive. Um, if A is of length n and B is also of length n, then A cross B is length n squared. So if n is 100, then A and B is 100, then A cross B is going to now be 1,000,000 rows. Okay, so things can cross products can be kind of expensive for this. It's all possible pairings. Okay, I think it's fine to say. Any questions about cross product? If they were different n values, would it be n times n? Yeah. Yep. So, I don't know, if n equals 4, then A could be, I don't know, SID, name, age, address. And now maybe B is something totally different. It's, I don't know, ISBN, title, number of pages, and author. Okay. So one's a table about people, A, and B is a table about books. N equals 4 for each of them. And now if you were to do A cross B, you would end up with a table that has an SID, a name, an age, an address, and an ISBN, and a title, and a number of pages, and author. Sorry, actually this isn't n. That's something different. But let's say that still n equals 4. So there's 4 ones here. 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, and 4, 4, 4, 4. So that has 4 entries, and the ISBN, I'll call it alpha, beta, gamma, and kappa. Then we would have 1, 1, 1, 1 here matched up with alpha. We would have 1, 1, 1, 1 matched up with beta. We would have 1, 1, 1, 1 matched up with gamma. We'd have 1, 1, 1, 1 matched up with kappa. Then we would have 2, 2, 2, 2 matched up with alpha, and 2, 2, 2, 2 matched up with beta, and blah, blah. This would have 16 rows. It would work like that. If we did a union on the boys and girls sets, do we just add girls to the bottom and create a boys-girls table? Yes, that is how it would work. So one thing to notice here, when I'm doing a cross multiplication, I'm expanding the table horizontally, right? So here we have these 4 things that appear here. But now that I'm cross multiplying it with B, then the table expands horizontally to include more fields. That is not the case with a union. Here, if we were to do boys union girls, then you would have a boys-girls table that would have name and age. And now there'd be 4 columns. So there's John, Paul, Susan, Anne, of age 18, 20, 19, and 21. So for the union, you're concatenating them like vertically. And this works because they're of the same type. They both have a name and an age. So the first column is a name, the second column is an age. So you kind of add them together vertically. You know, that's what a union does. It grows things vertically. Same thing with the subtraction or whatever. All of the ones that work with the same tuple, you're dealing with a table with the same number of columns. This is different with set multiplication, for example, where the table grows horizontally, and then you might have many more rows. But yes, good question. Okay. Fine. Okay. Okay. So the fifth operation is projection. And this is written with the Greek letter pi. And you'll notice a commonality here. The reason why we choose pi is because it begins with a p, and a projection begins with p. So we call it pi. A projection is the same type of projection that you might have learned about if you've ever taken a linear algebra course. So, a projection turns many coordinates into few. So for example, here if we have A that has columns A, B, and C, then the projection of this with A and C would be the projection of A where we only have columns A and C. Okay, so this is a way of sort of deleting a column. So here we would say this is dimension 3 because it has 3 columns, and we're reducing it down to 2 columns. So that is a projection. In maybe physics or linear algebra, you might have seen this as if you have like a vector that points in some direction, then the projection of it, this is like its shadow. Where this shadow only measures that direction. Or you could, shine a light from this side and have this projection, which would be a shadow going a different way. So this vector has 2 components. One component that goes left and right, and then another component that goes up and down. And you can isolate those components by sort of imagining shining a flashlight on this thing and then seeing where its shadow lands. Similar to that is this idea of a projection. So, but that's fine. That's one way of viewing it. Another way is you delete a column, or you delete some number of columns. That's a projection. Let me pick on somebody. How about Muskin? Muskin? Muskan? Muskan. Not around. Okay, how about Purva?
Yep, hi, Professor.
Hey. So, I want a projection on a set. This set. So there's going to be 4 elements. That's the first element 1, 2. Then we have the element 2, 3. And we have the element 1, 5. And we have the element 3, 4. Okay. So we're going to be projecting this set, and we're going to be projecting it where we only keep the first coordinate of this. So what would this equal?
So would it just be the 1 and 2? So like the first one, where x is 1 and y is 2?
Okay, so we're applying this to each element. So when we apply it to here, and you're keeping the first coordinate, what's the first coordinate of that element?
Oh, okay, so it's 1.
1, okay. And what's the first coordinate of, that second element?
2.
This one. Okay, so the first coordinate of that is 2. Okay, and the first coordinate of this one?
1.
Okay. And the first coordinate of the last one?
3.
3. Okay. Now another question is this correct? Is that a set?
Would it have to be like an ordered pair?
Not an ordered pair. There's something else about sets.
I think it looks okay.
I want to draw your attention to that.
Oh, there's 2 of the same. Okay.
So remember, a set is always as minimal as possible. So it's actually that set.
Yeah, okay.
Make sense?
Yep.
Okay, good. Yeah. Oh, sorry. Erase that for a minute. Okay, good. So this is an example of a projection. Okay. What are the values again? I'm sorry, I don't understand the question. Is that a 12? There shouldn't be any 12. So with, okay, so we have a set of 4 objects. Okay, those 4. The projection, so another way to view that set would be like this. Oh, I'm sorry, that's a 1, 2. Would be 1, 2, I don't know, we'll call it A and B. 1, 2 is a row, 2, 3 is a row, 1, 5 is a row, and 3, 4 is a row. Now when we project this and we're keeping the first coordinate, we're keeping that coordinate. So the result would be one table A that has 1, 2, and 3. Okay, 1 repeats itself, and we only need to have it 1 time because it's a set. That is to say that there's no repeats in any rows. You know, if we had another row here with a 1, that doesn't work because the rows need to be. These are all unique entries. Okay, so here on the left, this is sort of a set view of it. And here on the right, this is more of a table view of it. I think it's good to be able to go back and forth between the two. There's no, they're the same thing. And I will go back and forth myself depending on how I feel or which way I think is easier to understand the point that I'm trying to make. Okay? So a projection, you can think of it as deleting a column or deleting a dimension of the data. And that's it. Fairly straightforward, I hope. Okay. The next operation, what was that, 5? So 6. The next operation is select. And that's written with this symbol. It's not a 0, it's not a 6, it's kind of in between the two. And that is a lowercase sigma. In Greek. You might have seen the uppercase sigma for addition. This is a lowercase sigma. So that's like the Greek big S, and then this is the Greek little s. Whatever. The reason why we use this letter is because it's Greek and it begins with S. Okay? That's all. And this outputs a subset. That is to keep the row or the entry, or not. So, the way that the select works is you have some table, and the table has some entries. Whatever. And the select will delete particular rows. So maybe I don't like that row, it goes away. I don't like that row, it goes away. And so after the select, we might have A, B, and C with 1, 1, 1, and with 3, 3, 3. Okay, so the select works like it deletes rows. Okay, and what I mean by outputting a subset here is, again, if we have a set, and here we have 1, 2, 3, 4 points. 1 point is 1, 1, 1. Another point is 2, 2, 2. Another point is 3, 3, 3. And another point is 4, 4, 4. Then the output of our select is going to output these. Oh, sorry, circled one that I shouldn't have. Okay, that's the subset, which is just that. That is to say that here is a point or a row that we reject. That's another point or a row that we reject, and then everything that remains is what we keep. Let me pick on, how about Robin? Do you have a mic, Robin? Okay, then how about Serena? Okay, apparently I don't know what's up with Serena, but Robin, no problem. You don't have a mic. You can you can just write in the chat. So here I'll create a set with the same kinds of elements. We'll have 4 elements in this set. 1, 2, 2, 3, 1, 5, and 3, 4, just like above. Except this time, instead of a project, we're doing a select. So that is the set that we are performing the select on. And we want to select those elements where the second coordinate is even. So what is the result of this select? And you can just type it in the chat, that's fine. So we're going to be returned a set with some stuff in it. One, two, three, four. Yep. So we have the element 1, 2, and the element 3, 4. And that's it. Perfect. So from this set, we're keeping the ones where the second coordinate is even. So here, the second coordinate is 2. That's even, so we keep it. Here, the second coordinate is 3. That's not even, so we get rid of it. Same thing here. Second coordinate is 5. That's not even, so we get rid of it. This coordinate, 3, 4. 4 is even, so we keep it, and that's the result. Great. So that is the select. And there's technically 2 more, but I'll end on this one, which is really all that we need, which is the rename operator. So the rename is written with this. I don't know, it kind of looks like a P or something. I mean, it's not P, but with like a little swooped, left side. That's, as you might have guessed, another Greek letter that starts with a W. That's called rho. And by the way, these are the actual sort of letters that are used. If you don't like it and you just want to use the words rename and you don't want to use the Greek letters or whatever, I don't care. That's fine. But I'm going to be using them just so you can follow what I'm writing. So rename is very simple. This just renames a column. So let's say if I wanted to rename a column social security number, and I'm going to rename this employee social security number. And now I'll take as an argument, let's say, a relation that has an SSN and an age. Then this would return a tuple where the only thing that's changed is now this is called employee SSN and age. Okay, so rename is just a way to rename a column. Okay, and this is it. These are the 7 operations that comprise the algebra of relational algebra. Okay, there's 7 operations in total. Let's go through them again very quickly. We have operations where the tables need to have the same number and types of columns. This is a union. This is like taking one relation, like 2 relations, and you glue them vertically. That's like a union. An intersection is taking 2 relations and merging them together into one, where you keep the rows that exist in both of the relations. The set difference, you have two relations, and from one relation, you remove any entry that appears in another relation. That's called a set difference. Okay, those are the first three, and all three of these work on the same type of table. Same number of rows, same number of columns, same types of columns. Those are the first three. We have four more. One is the cross product. This is taking two relations, and for every entry of one relation, you pair it with every entry of the other relation. Okay, this is an expensive operation, this one. But it's required sometimes, and so you can't avoid it. That's the cross product or multiplication, if you like. Then there's the projection, which is when you reduce the number of coordinates, or otherwise you delete some columns. There's select. So project deletes a column or columns. Select deletes rows or keeps rows, depending on the way you want to view it, whichever. Does a string and an integer count as the same type, or is that different types? Those are different types. A string and an integer are different types. So what I mean by type is, there could be a string, there could be an integer, a float, a Boolean, types, kind of like Python. Can you, can you do ABC minus 1? Does that make sense? No, different types. That's a string, that's an integer. So they conflict. Can't, different types. That's all that I mean by the types. Okay. So projection deletes a column, select deletes a row, and rename just renames a column from one thing to another. That's it. These are all of the operations that are that are needed to do algebra with relations. I will leave you today with a sort of practice problem, I guess, which is one extra operation that the book uses and other sources use will be about joins. If you've taken SQL before, or if you know about certain relational database things, you might have heard of a join. There's something called a natural join that's written as like a bow tie. And this selects or filters entries with a common attribute. So, for example, if we have A that has name, age, and we have B that also has name, age, well, I'll say name, address, whatever. Okay, here we have John and Paul, and here we have John and Susan. Okay, and if we wanted to do a natural join of A and B on name, then we would be selecting and combining these tables where the result would be name, age, and address. Where here, John, because John appears in both of these tables, we want to join it together and now know everything about John that we can. So from table A, we know his age, 18, let's say, and we know his address, 1 Avenue, 2 Street, whatever. And so he lives on 1 Avenue, okay? And that would be the result of the natural join. So a natural join takes one or more or two or more relations and combines them together according to the commonality of some attribute. In this case, both of these tables share the name John, so we'll combine those together, and this is the result. Now, the thing that I'll leave you with is that we do not need the join here. You can recreate this operation using a combination of these above 7. You can use a combination of union, intersection, set difference, cross product, projection, select, and rename. Those are all of the ones that you actually need, and then you can actually reproduce this natural join. So in this course, we will not be talking about natural joins. We will be replacing them with the lower level operations. And by lower level operations, I mean all of these 7 up above. So that is your practice problem, if you like. Natural join is not the same as an intersection. In fact, this intersection couldn't work because one is an age, which is of a type integer, let's say, and the other is an address, which would be a string. So you cannot intersect these. They are not of the same kind. It's sort of related to an intersection, but it's different. And yeah, so that's your practice problem. I don't want to keep you. You can log off if you like. I'll hang around for questions, and have a good week or a week.